Okay? So today we're going to talk about the uniform distribution and the normal distribution. So we talked about this in the last lecture as well. We say that X has the uniform distribution in some interval between A and B if the points in this interval are equally dense. Okay? So do you remember in the discrete case, if I say, hey, X has the uniform distribution, which takes the values 1, 2, and 5. What do you think? What are the probabilities? 1 over 3, right? So all the probabilities should, all the outputs should have the equal chances to appear, right? In this case, we say the X has the uniform distribution. So in a continuous case, so if I say that X can take any value between A and B with equal chances, then how the density function should look like? It should be just a horizontal line, right? So the chances that every single point in this interval, between A and B, appear are the same, right? They're equally dense in this interval. Now, I know the width, so the area under this curve should be equal to 1, right? So this area should be equal to 1, right? So what is the width of this rectangle? What is the width? So this is B minus A, right? So if I multiply the width of this rectangle to the height, it should give me 1, right? So what is the height? So this is 1 over B minus A, right? So that is why the density function of this random variable will be equal to 1 divided to the B minus A if X is between A and B, and 0 otherwise. Okay? So later on, we'll talk about the cumulative distribution function. The cumulative distribution function means the probability of a random variable X takes the values until the C. What is the probability that X is the until the C? So what does it mean in the discrete case, in the continuous case, how we need to calculate this? We need to again integrate the density function in this interval, right? What is this interval? It's from minus infinity to the C, dx, right? Geometrically, it means that if your curve is given like this, if you choose one point C, this is the area under this curve until this point C, right? This gives you big F of C, the cumulative distribution of C, okay? So this is an important function in the continuous case because later on we will discuss how to get the density functions from the cumulative functions, okay? So you've seen from the quiz that the density function is really important in continuous case because we can find all possible probabilities or all possible features of the random variables using the density functions, okay? So let me first of all write down the cumulative distribution function for the uniform distribution. So let's say if I choose 1x from here less than A, what will be the area until this x? It will be 0, right? No matter what is the x, if it is less than A, this is the area until this point will be 0, right? Because the density curve is 0 until the A. Between A and B, this is 1 over B minus A, and after the B, it is 0 again, right? So if I choose any point before the A, the area until this point will be equal to the 0. Now, if I choose some point x here, what will be the area until this x? This area will be the area of this rectangle, right? So the area of this rectangle is nothing else, is the multiplication of the widths, right? What's the width? Is x minus a, right? To the height of this rectangle, which is 1 over b minus a, right? So if you choose some point between a and b, then the cumulative distribution function will be equal to the x minus a divided to the b minus a. Okay? If x is more than b, what will be the cumulative distribution function? If, for example, you choose some x here, what will be the area until this point x? 1. Right? So for any point which is bigger than b, the area until that point will be equal to the 1. Okay? So the importance of this cumulative distribution function is that its derivative is equal to the density function, okay? Or the antiderivative of the density function is the cumulative distribution function, okay? So it comes from the fundamental theorem of calculus. So by the definition, big F of x is equal to the integration from minus infinity to the x, right? Yeah, by the definition, this is the probability until this point x, right, of the density function. And what does the fundamental theorem of calculus 1 tells us? It tells us that if my function is like this, where the variable x is not inside the integration, but on the borders of the integration, then the derivative of the big F gives you the small f of x, right? This is what does the fundamental theorem of calculus tells us, okay? So this function big F is important because this is the antiderivative of the small one, right? We can check it from this example, right? If you take the derivative of this big F, what you will get? So derivative for the regions where the x is less than a, so let's find the derivative. For the regions x is less than a, what will be the derivative of the 0? Simply 0, right? For the regions x is between a and b, what will be the derivative of this one? Is 1 over b minus a, right? You can split this as x over b minus a over b minus a. Derivative of the second is 0 because this is the constant, right? And derivative of the 1 is also 0. For all the regions, x is more than b, it's also 0, right? Which is exactly the density function, right? So do you see? So it is important because later on we will try to get the density function from the cumulative distribution function, okay? Now, let's do an example. Let's say the buses arrived at the station near your house every 15 minutes, starting 7. They arrive at 7, 7:15, 7:30, 7:45, and so on, okay? So usually when you come to the university, you might come to the station at any time, at any random time, between 7 and 7:30, okay? You might come at 7:15, 7:13, any time between 7:00 and 7:30 with uniform distribution, okay? It means that the chances that you will come at any time between 7 and 7:30 are the same, okay? Now, you come at some point x, what is the probability that you're going to wait less than 5 minutes for the next bus? Okay, this is the first question. And the second question is, what is the probability that you're going to wait more than 10 minutes? Okay, so let's do the first part together, and you need to try to do the second part by yourself. So x, it is given that x has the uniform distribution between 0 and 30, right? So if it is like this, what will be the density function of the x? So this will be 1 over b minus a, which is 30, right? For all the values of the x between 0 and 30. So it is really important for every problem which we're solving to understand what is the random variable, okay? So in our case, the random variable x means the time when you arrive to the station, okay? It may change from 0 to the 30, and it has the uniform distribution, okay? So that is why its density function is like this. For all the other values, it is 0, okay? Now, but we're asked about the waiting time, right? What is the probability that you wait less than 5 minutes, right? Waiting time, which is not our random variable x, right? Our random variable x is when you come to the station, not how much time you need to wait, right? So is it possible to express the waiting time using the time when you arrived at the station? in which interval you need to come to the station so that you will wait less than 5 minutes for the next one. From 10 to the 15, right? If you arrive between 10 and 15, you're going to wait less than 5 minutes for the bus. And if you arrive between 25 and 30, or in this case, you also wait less than 5 minutes, right? So we can rephrase our question, right? But instead of asking, what is the probability that you're going to wait less than 5 minutes for the next bus, we can ask, what is the probability that your arrival time is between 10 and 15 or 25 and 30? These three questions are equivalent, right? Okay, so we need to find the probability. It doesn't matter. So in a continuous case, it doesn't matter because like probability of the random variable gets the specific points is equal to the 0. Okay, it doesn't matter whether you take it as equal to the 0 or not. Okay. So what will be the probability that x is between 10 and 15? This is the integration of the density function between 10 and 15 plus the integration of the density function from 25 until 30. Right? So what was the density function? It's 1 over 30, right? So you just need to integrate 1 over 30. If you integrate 1 over 30, what you get? What's the antiderivative? It's x over 30, right? We need to put the values from 10 to the 15, plus again x over 30 from 30 to the 25. So this case will be equal to the 5 over 30, plus this case is again 5 over 30. So the answer is 1 over 3. Okay, could you please quickly by yourself tell me what is the probability that the waiting time is more than 10 minutes? Quickly. So can you rephrase this with the arrival time? So what's the arrival time? Can you rephrase this question? What is the probability that you're going to wait more than 10 minutes? Rephrase this question with our random variable, with arrival time. So you can ask, what is the probability that you will arrive between 0 and 0, 5, right? 0 and 5. Or between 15 and 20, right? Okay, this will be the same, right? So the probability that you're going to wait more than 10 minutes is finding the probability of arrival time between 0 and 5, right? Or finding the probability between 15 and 20, right? So if you integrate everything, you will get again 1 over 3, okay? Probability that you will wait less than 5 minutes is equal to the 1 over 3. And the probability that you're going to wait more than 10 minutes is also 1 over 3, okay? So here it is really important that, for example, in the first case, in the second case, you can include basically, in the first case, you would include the case when you arrive exactly at 700, right? But we know the probability that you arrive exactly at 70 is equal to the 0, okay? So you need to try to understand that theoretically it is like this, okay? So you cannot feel like, maybe it's like not logical, right? But like this is like the theoretical. So we can just explain this like in the longer range, okay, it is true. Okay, so in the previous grid, one student asked me, so if you claim that the probability is the area under the curve, right? Then if you claim that the probability at the single point is equal to the 0, why then the summation of all the probabilities gives you a positive number, not 0? Why? So he's asking me, if the probability at the single point is equal to the 0, why then if you take the summation of all the probabilities, it is more than 0? Okay, so this comes actually from the definition of the integration. Okay, so if you're given the curve, what is the integration, by the way? This is just the limit of the Riemann sum, right? So what does it mean? It means that if I would like to integrate this function between a and b, I need to try to do this numerically, right? So I will split this interval between a and b to the many small rectangles, right? For example, to this one, then for this one, then for this one, and so on, right? Then I will find the area of each of the rectangles and I will sum them, okay? So what will be the area of the first rectangle? So this is this point, right? What is the coordinate, y coordinate of this point? Y coordinate of this point. F of a, right? So this is f of x. At the point A, the y coordinate of this point, the first point, is equal to the f of a, right? So the area of the first rectangle is f of a multiplied to the delta x, right? Then you will find the area of all the rectangles, then you will add them, right? So if you take the limit when this delta x becomes equal to the 0, limit, right? Then it gives you the integration, right? The definite integration. Now, if you claim that, hey, why I cannot just find the area by taking this interval, do you see? So this delta x to be equal to the 0, just exactly to be equal to the 0, right? So let's make it. So this is f of a, right? Now the delta x is equal to the 0, okay? Even if you take really a lot of points, right? A lot of points. What will be the area of this first rectangle? So this is f of a multiplied to the 0, exactly 0, right? Okay? If you add all of them, you will still get, again, a 0, okay? So this seems kind of illogical, but it's like this. So you cannot find the area between a and b by taking the rectangles with the width to be equal to the 0, okay? So that is why if you add the probabilities in the spatial points, even if you take a lot of points, the sum gives you again 0, okay? So you need to get this delta x to be some number which is not 0, but in the limit it should be equal to the 0, okay? So the meaning of the limit is like, so it is really close to the 0, but not 0, okay? If you could just substitute the delta x with a 0 always, then we would not need the limits, right? We would always put the 0 instead of delta x, okay? The meaning of the limit is like this. So it is really close to the 0, but not 0. If you take a 0, exactly this point, okay, then the summation gives you 0, okay? The integration will be equal to the 0. So the probability at a specific point is equal to the 0, okay? That's the conclusion. Now let's start talking about the normal distribution. So the normal distribution was introduced by de Moivre. So there was a formula on the complex numbers from calculus, which is called the de Moivre's formula, or engineering maths. You probably have learned about this as well. So he used the normal distribution as the approximation of the binomial distribution. So do you remember previously we said the Poisson distribution is the approximation of the binomial distribution, right? But the Poisson is the discrete case again, okay? So the normal distribution is the same, is similar to the binomial distribution, but in the continuous case, okay? So the binomial distribution, the normal distribution is really important because many things which are around us, which are random, can be explained using the normal distribution, okay? For example, the height of the man can be explained using the normal distribution. We can make the graph. Or can you make me the question, probabilistic question, about the height of the man? So let's assume I will choose one of the students randomly, and I would like to know what is the probability that his height is between 160 and 180. What is this probability? So in order to find this kind of probabilities, I need to know the density function, right? So we model this kind of situations using this kind of density function, which is called the bell-shaped curve. Bell-shaped curve. So you can understand this like this, okay? So this is not the meaning exactly like this, but you can understand this like this. You can say, okay, so this curve, the height of the curve, tells you the frequency, okay? So in our university, how many students have the height? Around 1.67. Probably a lot, right? very few students have the height 140 or 150, right? And very few students have the height 2 meters or over, right? So you can see this as a frequency. You can understand this as a frequency, okay? So which is the normal situation, right? Okay? Now, if I would like to find the probability that the height of the randomly chosen student is between 160 and 180, I just need to find this area, right? It gives me the probability. Or, for example, so you probably did a lot of experiments in physics, right? And whenever you do that experiment, you need to find the error which you're making in your experiment, right? How do you do this? So there is a theoretical result, which you calculated theoretically, right? Then you do your experiment, you get this result, and by finding the difference, you will find the error, right? So obviously, if you do the experiment many, many times, most of the time, you might get different errors, right? So the error which you're getting is the random variable, right? And which is continuous random variable, because every time you're measuring this thing, and the error is all the time, might be different, okay? Then we can express the density function of this error, again, using this kind of curve, right? Again, we need to understand that this curve is kind of the frequency, okay? So most of the time, you might get the error 0.1. Sometimes you might get bigger error, or sometimes you might get a smaller error, okay? Again, so if I ask you the question, what is the probability that next time when you do the experiment, you will get the error between 0.09 and 0.11, you again need to find this area, okay? So you see so many cases, many different cases can be explained using the normal distributions, okay? Or this kind of bell-shaped curves. So let us write down the density function. So x, the random variable, is called the normally distributed. Whereas the parameters mu and sigma squared. If the density of this x is given by this formula. So sometimes we call this function as a Gaussian function as well. So here mu is the mean, so average value of the x, okay? And sigma squared is the variance, okay? So sigma squared is the variance. Sigma squared is the variance. Do you remember? So we just found the variance in the beginning of this lecture, right? And the sigma is called the standard deviation. Okay, could you please write this down? So sigma is the standard deviation. Sigma squared is the variance. So what do you think? What is the difference between sigma squared and sigma in terms of its meaning? What is the difference between standard deviation and the variance? There's no difference. Okay, they both means the same thing. Okay, they both means like it measures how the points are far away from the mean. What is the average distance from the mean? Okay, so since we measure this variance relatively, it doesn't matter whether you take the square root or you take the square and so on. Okay, so the meaning of the standard deviation and the variance is the same. No, sigma is not under the square root. Sigma is separate from the square root. 2 pi from the square root multiplied separately to the sigma. Okay, actually, you don't need this formula. I mean, it's really big, and we're not going to use this formula to find the probabilities. So in calculus, we talk about the transformation of the functions, right? So it is really difficult now probably for you to understand how the function, the shape of the function changes when we change the mu and the sigma. Or let's try to do this from their definition. So let me write x in f of x. So our f of x is equal to 1 over sigma multiplied to the 2 pi e in the power of minus x minus mu in the square divided to the sigma square. Okay? So, or 2 sigma square, right? 2 sigma square. Now, okay, so if you put the x to be equal to the mu, you will get some value, right? What value you will get? If you put x to be equal to the mu, you will get 1 over sigma multiplied to the square root of 2 pi, right? This will be the maximum point of this curve. Okay? Because no matter which x you will take, you will put here instead of, if you put any other value, this will make this value smaller. Okay? Because this is 1 over e, 1 over some positive number. It makes the overall function smaller. So at the point mu, our function has its maximum point. Okay? Now, if you change the mu, how the curve is changing? For example, if you shift the mu to here, for example, it was 50. Now, you take the 60 and put this to the function. The curve will be just shifted. Okay? It will be, again, the same curve, but shifted to the 10 units to the right. Okay? If you change the mean to the left, it will be just shifted to the left. Okay? Now, if you change the variance, how it changes? If you change the standard deviation. So the standard deviation, what does it mean? It means how the points are far away from the mean, right? If the variance is bigger, it means that the points are more far from the mean, right? So it means that as much we increase the variance, the curve will be more flat, right? So for example, if this curve has one variance, sigma 1, one standard deviation, sigma 1, and if this curve has another variance, sigma 2, which one is bigger? Sigma 1 is bigger than sigma 2. Right? You understand us from the concept, right? So more flat means that the points are more far away from the mean, right? More steeper, it means that the points are really close to the, there are a lot of points around the mean, right? Okay. Let's do an exercise. So let's say there is a company which repairs the air conditioners, which just set up the air conditioner, okay? They come to my house, or they might come to your house and set up the air conditioner. Usually it takes some time. Sometimes it might take 5 minutes, sometimes it might take 15 minutes. It depends really on the situation, right? But this is random, okay? And let's assume that this random variable has a normal distribution with the mean 10 minutes. Usually it takes 10 minutes until they set up everything, and with the standard deviation of 5 minutes, okay? So if they come tomorrow to my house at 15:00, what is the probability that it will take less than 15 minutes until they will set up everything with my air conditioner? If they come at 15:00, what is the probability that it will take less than 15 minutes until they set up everything? We should use, yes. So if I would like to, yes, so if I would like to find the probability, we need to integrate the density function in the interval, right? From where to where? From 0 to the 15, right? So in the slides there is a typo. It should be integration from 0 to the 15. So the probability that it will take less than 15 minutes, it will be this integration, which is impossible, right? Like analytically, we cannot solve this, okay? So what we can do is we can try to solve this numerically, right? Since you're engineers, you need to tell me how to evaluate this probability. So can we evaluate the function's value? Do you understand this? So if I give you x, can you tell me f of x? With the computer? Yes? You can do this, right? Okay, just using this information, we can find this integration numerically, right? By splitting this to the many rectangles, right? And finding the areas. Okay. But which is still difficult, right? I would say. Really difficult. So what to do? Nothing. Okay, so which would be difficult? I mean, which is doable if you have the computer, right? You can open the computer and you can do this, but which is like, so since you're engineers, you need to like try to figure out the way how to avoid this, right? Okay, so the idea would be like this. So, did I tell you the story about the ACM? With the prime numbers? So, in the ACM, there was a championship in programming. they give you the problems. You need to write a program and send them to them, okay? Your program should work, but not only work, it should work in optimal time, fast, and it should require less memories, okay? There was a problem. They asked to identify whether the input n is the prime or not, okay? For example, if they give you 25, you just need to tell yes or no, whether this is the prime or not, okay? So how you can do this? What is the algorithm? You need to start dividing the numbers until the square root of this n, right? If any of the numbers are divisible to this number, then you say that this is not a prime, right? If none of them are divisible, then you say that this is the prime, right? For example, if you choose 17, you start dividing 2, 3, 4, right? Square root of 17 is like 4, the maximum, right? If you divide all of the 3, none of them are divisible, right? It means that 17 is a prime, okay? Now the problem is like this. So if I give you really big n, then your program may not pass from the time requirements, okay? So either in a short time, like in 15 minutes, we need to figure out a really good algorithm which identifies whether n is prime number or not. Either we can try to cheat, right? How we can cheat? Huh? List out all the primes, right? So just go to the Wikipedia and copy all the primes until the n, right? Make the array. Make the array with all the primes, okay? 2, 3, 5, 7, and so on, okay? And whenever you input the n, instead of identifying whether this is the prime or not, you can just search this n in your area, right? Which obviously requires less time, right? You will just search this n inside your area. If you find this n, you say, okay, this is the prime. If you do not find this n inside your area, you say that this is not a prime, okay? You can do this beforehand, right? So when you send a program, yes, so you make the program. You were given, for example, half an hour. And in this time, you can copy everything, do whatever you want. So when you send a program, it should work. It should tell whether the n is prime or not, okay? You can cheat like this, okay? So why I'm telling this story? Because we need to do the same thing now, okay? So if you're given, no matter what kind of normal distribution, do you see? So all of them are bell-shaped curves, right? But depending on the mu and sigma, their graph might be different, right? So the idea would be to kind of transfer all of them to one curve, which is called the standard normal distribution. Which has the fixed mean, which is equal to the 0, and fixed standard deviation, which is 1, okay? And try to figure out to which area, for example, if I need to calculate this area, what area it's correspond in the standard normal distribution, okay? This is the only thing which I need to figure out, okay? So the areas for this standard normal distribution are given in the table. So some people numerically calculated all possible areas for the standard normal distribution, okay? So the area is given for every single point, okay? Now what we need to do is, if we're given the problem on the normal distribution, we need to kind of transfer our normal distribution to the standard normal distribution. Basically find those 2 points which corresponds to here, okay? And figure out the area from the tables, okay? From the tables of the areas. So some people have calculated all possible areas numerically and made the table. We're just going to use this table. Yes, we really have a table in the appendix of the book. We're going to use this table in order to calculate the probabilities, okay? Because like calculating the probabilities by integrating in a continuous case is really difficult, okay? So we will do this next time, okay? So let's finish for today. Just keep the silence.